So here's an exercise that we can do, and maybe here's also the moment where you should push the pause button, because it's always better when you do the exercise by yourself, or that you at least try to do it by yourself. So this is a first order differential equation where the input f of t is given using a drawing and not given explicitly, so you have to reconstruct it, and here you'll have to do this using step functions. Okay, so this is why you should not neglect the exercises that are on the exercise web page that is associated to the course, and these are sections 2 and 3 when you learn the basics of signals and systems. So let us start the exercise, and we first start by finding a mathematical expression for f of t. So you'll have two steps over here, one in t equals 0 and one in t equals 1, and it will give you u of t minus u of t minus 1, and 2 to have the correct amplitude. So this is something that you know. We've done something similar when we talked about the rectangular impulse. So what we can do now is go to the Laplace domain. So what we'll have is sys minus the initial condition plus 3 times ys, and on the other side we have the Laplace transform of f of t. This will have Laplace transform 1 over s, so it will be 2 over s, 1 minus, and here there is a time shifting, so we'll have e to the minus s over here. Okay, so this we can rewrite, so this will be a 1 over here. We can put everything with a ys together, and this will give us s plus 3 ys. The minus 1 will take it on the other side, so it will be a 1 plus 2 over s, 1 minus e of minus s. Okay, so you can rewrite y of s as 1 over s plus 3, okay, plus 2 over s plus 3, 1 minus e of minus s. Okay, this looks right, and this is the 0 input response, and this is the 0 state response that comes from the input, and this is the 0 input response that comes from the initial conditions, right? So what we need to do now is kind of write this in partial fractions, but you have to pay attention. What I often see at the time of the exam is that, students write this as something a over s plus b over s plus 3, and they do this for the whole term over here. This will not work because of the e minus s. Okay, so you have to kind of rewrite this as follows when you group all the terms that involve e minus s. So you can write it like this: 1 over s plus 3 plus 2 over s times s plus 3 times the 1 over here, and then plus 2 e to the minus s over s times s plus 3. Okay, and now you can do a partial fraction expansion for this one and a partial fraction expansion for this one, and you leave this one as a factor. So we'll have to do the partial fraction expansion of 2 over s plus 3. We'll write it as a over s plus b over s plus 3. A is, well, we multiply by s, so we have 2 over s plus 3 evaluated in s is equal to 0, so that's 2/3, and b will be 2 over s evaluated in s is equal to minus 3, so this is equal to minus 2/3. Okay, so you can write it as 2/3 times 1 over s minus 1 over s plus 3. This looks correct. Okay, how do you check that? Well, you put everything on the same denominator and you can see that this will be okay, right? So now what do we have here? This is still y of s. We'll have y of s is equal to 1 over s plus 3 plus 2/3 1 over s minus 1 over s plus 3 and plus 2/3 1 over s minus 1 over s plus 3 times e to the minus s. And what we can do now is do the inverse Laplace transform. So we have y of t, so this is e to the minus 3t u of t. Okay, so this was the 0 input response. So in French this is la réponse libre, and then we'll have 2/3 1 minus e minus 3t u of t, right? And we'll have a similar term over here, right? Oh, here it's a minus, of course, huh? You didn't tell me. So it's a minus, and I will have, of course, a minus over here. Minus 2/3 of e to the minus, and here we have to pay attention, 3t minus 1 u of t minus 1. Okay, and this is the 0 state response, and in French it is la réponse forcée. Okay, so what we have to check over here is if we meet the initial condition in y of 0. So here we'll have 1, and here we'll have 0, so it is correct. So here we have solved our first exercise. So here's another exercise, and it's one of the type that I like very much, and it says, well, the response of a system to the input x of t is exponential of minus 2t times u of t is y of t. It's equal to this expression over here, and then the question is, can you find the impulse response and the step response? Okay, so first thing that we have to do is maybe find the transfer function of that system, and you can simply do this by writing h of s is equal to y of s divided by x of s, right? X of s is the Laplace transform of this signal, and that's 1 over s plus 2, and y of s is, well, 1 over s plus 1 plus 1 over s plus 3, and if we put that under the same denominator, we'll have s plus 1 s plus 3, and at the numerator we'll have 2 times s plus 2. Okay, so h of s will be 2 over s plus 2, s plus 1, s plus 3, that's y of s divided by 1 over s plus 2. So this is 2 times s plus 2 squared over s plus 1 s plus 3. Okay, so this is the transfer function, and it's the characteristic of the system. And now we can start answering the question. So we know that the impulse response we can obtain by taking the inverse Laplace transform of h of s, and this will be h of t. Okay, so here we have to pay attention because this transfer function is not strictly proper. So before we do the inverse Laplace transform, we have to do Euclidean division. Okay, so this one we can write it as follows. It's 2s squared plus 8s plus 8 divided by s plus 1 s plus 3. Okay, so let us do this Euclidean division. So we take this one and we divide, well, this one also we have to expand it, and it will be s squared plus 4s plus 3, and here we have to divide the numerator polynomial by the denominator polynomial. So it will enter 2 times in this one, so we have 2s squared plus 8s plus 6, so we subtract and we end up with a 2 over here. Okay, so we can rewrite h of s as 2 plus 2 over s plus 1 and s plus 3, right? And now we have to do the partial fraction expansion of this one. So it will be 2, okay, plus a over s plus 1 plus b over s plus 3. So let's hide this one over here and replace s by minus 1, and we have a 1 over here. So now we know that the a is a 1. Oh. And the b, let's hide the s plus 3 and replace the s by minus 3, so b is a minus 1. So we have minus 1 over here. So this is still h of s, and now we can do the inverse Laplace, and we have h of t is, well, the inverse Laplace transform of a constant signal means that we have a 2 times delta. Remember that the Laplace transform of a Dirac delta impulse is a constant 1, so here we have 2 of them, and we have plus e to the minus t minus e to the minus 3t u of t. Okay, so this is the impulse response, and now what we can do is kind of compute the step response. Okay, so we have already decomposed things, so we can use this here, right? So we'll have that y of s is h of s times x of s, that is h of s multiplied by 1 over s, because we're considering now the step response. Okay, so this will be 2 over s plus 2 over s, s plus 1, s plus 3, right? So we can rewrite this as 2 over s plus a over s plus b over s plus 3. No, take s plus 1 plus c over s plus 3, right? So a is 2 over s plus 1, s plus 3, evaluated in s is equal to 0. So this is 2/3. B is equal to 2 over s, s plus 3, evaluated in s is equal to minus 1. And this will be minus 1. Let's check again. Yeah, that's correct. And c will be 2 over s times s plus 1, evaluated in s is equal to minus 3. And this will be 1/3. Okay, so we have here a 2 and a 2/3, so this will be, let's make some order over here. So if we put these two together, it will be 8/3 minus 1 over s plus 1 plus 1/3 over s plus 3, right? And now we can do the inverse Laplace transform, and the step response will be, I forgot the s over here, 8/3 minus e to the minus t plus 1/3 e to the minus 3t times the unit step to make the whole thing causal. And this is the step response of the system. So here's another exercise. It's a second order differential equation. So there are 2 initial conditions. So in order to go to the Laplace domain, we need to kind of find the Laplace transform of the second derivative of a function. So we know that the Laplace transform of the first derivative is given by sys minus y0, right? And we know that the Laplace transform of the second derivative will be s times the Laplace transform of the first derivative minus the initial condition in the first derivative at time t equals to 0. So this is exactly the same equation as the first one. Okay, you see that here you take the, this is the Laplace transform of y of t. Okay, so it's the Laplace transform of the integral of this signal, and so this is exactly what we do over here. So now what we can do is plug this in here, and we have s times sys minus y0 minus y prime 0 is equal to s square ys minus s y0 minus y prime 0, right? So we can write this over here. Let's erase this so that we have some place to write. So it's s square y of s minus sy 0 minus y prime of 0 plus, so here maybe we can put parentheses, plus 16 y of s, that's the Laplace transform of this one, second term, and then we need the right hand side. Okay, so let's see if we can obtain that. So we know that the Laplace transform of cosine 2t u of t, well, that's the Laplace transform of a half times e of minus 2jt plus e 2jt, the whole thing times ut. So this is the Euler identity. By linearity, so what you have is 1/2 Laplace transform of e to the minus 2jt u of t plus Laplace transform of e to the jt u of t. So this is a half 1 over s plus 2j plus 1 over s minus 2j. We put everything under the same denominator. If you're going to multiply these at the denominator, you'll have s squared plus 4, and here at the numerator s minus 2j plus s minus 2j, and we obtain s over s squared plus 4. So we can plug that in over here. Okay, so we've taken the differential equation and we've kind of transformed it after Laplace transform. Okay, so what we can do now is collect all terms in ys. So this will give me s squared plus 16 times ys. Well, this one is a 1 over here, and this one will not give any contribution. So if we take it to the other side, we have a s over here. And here, of course, you've probably seen it. It's 3 cos, so we need a 3 over here, of course. Okay, so you see that when you do an exercise, it's worthwhile stopping at some stage to see if you haven't made any mistakes. Okay, so y of s is equal to s over s squared plus 16 plus 3s over x squared plus 16 plus s squared plus 4. Okay, some of you will want to put this under the same denominator. My question is then, why would you do that? Okay, you'll obtain a rational fraction which will be much more difficult to decompose, so I would leave it as is and write y of s is equal to s squared plus 16. Well, you know that's the Laplace transform of a cosine. Okay, plus, and then we can do the partial fraction expansion here, and we'll have a term. Okay, so we have a fourth order, so we expect, well, 4 constants in the partial fraction expansion. So the numerator will be first order. You remember that this needs to be, well, of relative degree 1, so it's as plus b, cs plus d, right? So you can see here that the terms in, or the coefficients b and d will be 0 because they can only create independent terms and terms in s square. Okay, and in here you see that there is 3s, so you can kind of see already that b is going to be equal to 0 and d is going to be equal to d. So if you don't believe me, well, we'll go through the calculations, and what we'll do here is write the terms in s cube, and it will give us a plus c, and I don't see here on the numerator any term in this cube, so that's a 0 over here. We can now take the terms in s. In s we're going to have, well, 4a, right, plus 16, c is equal to 0, right? So what we can do here is, well, take this one and subtract 4 times this equation, and what will, well, that's not a 0, right? That's a 3, right? So it's a 3 over here. So this equation times 4 times the first one, and we'll have 12c is equal to 3, right? This is c is equal to a quarter, and this means that a is going to be minus a quarter. Now we can have a look at the terms in s square. So we'll have b plus d is equal to 0, and we'll also have 4b plus 16 and d is equal to 0, and this will lead to b is equal to 0 and d is equal to 0, right? Okay, so now we can write y of s. So s squared plus 16. Okay, so what do we got here? So in the terms minus a fourth s squared plus 16, and we have a s, of course, over here, plus a quarter s squared plus 4. Okay, so we can put these two together, so we have 3/4 s over s squared plus 16 plus a quarter s over s squared plus 4. You remember that we've done it at the beginning of the exercise. This is the Laplace transform of a cosine. Okay, the cosine of the square root of this one, 4t, right? And this will be a cosine 2t. So if we now go to the time domain again, so we do the Laplace transform inverse. What we've done over here is the Laplace transform. So we return to the time domain. What we'll have is, well, 3/4 of cosine 4t okay, 4t plus 1/4 of cosine 2t, the whole thing times the unit step, because we want to make it causal, and this is y of t, my solution. Okay, are we done? No, we're not. We have to check if this solution meets the initial conditions, and indeed, since you know that the cosine of 0 is 1, you'll have that y0 is 3/4 plus 1/4, that's 1. And if you take the time derivative, okay, well, this will involve sines, okay, and a sine at t equals 0 is 0, so indeed the derivative will be 0. So now we're kind of finished. So here's another exercise. It's again a second order differential equation. So as usual, we have, of course, two initial conditions on the output at time 0. And well, right now is maybe the moment to push the pause button so that you can do or try to do the exercise by yourself. Okay, so as usual, we have to go to the Laplace domain. Okay, so we need the Laplace of the second derivative. Okay, so we remember that the Laplace of the first derivative of y of t is, well, s times the Laplace transform of y of t minus y0. So the Laplace transform of the second derivative is the same as this equation, but since you have taken the derivative over here, so you'll have s Laplace transform of the derivative minus the initial condition at the derivative. You can plug this in here, so we have s y of s minus y0 minus the derivative on the condition on the derivative. So this is s square y of s minus s y0 minus y prime 0. Okay, so it takes you about a minute to find this expression, so it's better to find it than just to learn it by heart and make a mistake, right? So we have s square y of s minus s y0 minus the condition on the derivative. Let's put some parentheses here and we can now erase this. And we have 2 times, and there also put parentheses, sys minus y0. We close the parentheses, and here we have, well, 2 times the Laplace transform of a step, and that we know that it's 1 over s. So this is what we obtain. Okay, the reason why it's better to put the parentheses is because 2 also multiplies this one over here, and at the time of the exam I very often see mistakes. Parentheses is not written and this one does not get multiplied by 2, which leads to a mistake, of course. Okay, so what have we got here? We have well, we'll collect first all terms. Oh, important to check, what did we forget? Oh, what did I forget? It's this term, which is the Laplace transform of this one over here. Okay, so now we can collect all terms in ys. So it's s squared plus 2s plus 2 y of s. This will give me minus s minus 1. Okay, and this will give me minus 2 is equal to 2 over s, sorry, and we'll write it a little bit differently. We'll write it like this: 2 over s plus 3. Okay, so this looks correct. So we can write y of s, it's 2 over s squared plus 2s plus 2 plus s plus 3 over s squared plus 2s plus 2. So you might put it under the same denominator, but well, it doesn't really bring anything. So what I'll do is decompose this one as a over s plus b over s plus c over s squared plus 2s plus 2. Okay, remember over here the denominator is a third order denominator, so we need 3 constants: this one, and this one, and this one, right? So a, we can obtain it as follows. So a is, well, 2 over s squared plus 2s plus 2 evaluated at s is equal to 0, so that will leave me a 1 over here. And what we can do in here is kind of look at the terms in s squared. So this will give me a, right, and also plus b, and here in the numerator I don't see any terms in s squared, so that's a plus b is equal to 0, so b is equal to minus 1. And let us have a look at the terms in s now. So there will be a times 2, so 2a plus c. Okay, and again I don't see any terms in s over here, so it's 0. So this leaves us with a c that is equal to minus 2. Remember that this is equal to a over here. So we have a, b, and c. What you should do is maybe, well, put everything together again and see if you have not made any mistakes, right? So y of s is equal to 1 over s, and then, oh, well, c, this is incorrect. Again, you didn't tell me anything, so it's a minus 2, of course, over here. Okay, so we have minus, and we'll have s plus 2 over s squared plus 2s plus 2, right? And we'll have this one over here plus s plus 3 s squared plus 2s plus 2. So this is equal to 1 over s, and this leaves us with, well, plus 1 over s squared plus 2s plus 2. And in order to do the inverse Laplace transform, what we'll do is take this denominator and complete the square. So you can also write it as 1 over s plus 1 over, so we'll construct the square, the first square of based on s squared plus 2s, so this will leave us with s plus 1 squared. Okay, so if we square the 1, we have 1, we have a 2 over here, so we need to add a 1 over here. Okay, so why do we do this? Well, because in this we recognize the Laplace transform of a sine, that it will be multiplied by an exponential. Okay, so remember that the Laplace transform inverse of 1 over s squared plus 1 will be sine of t u of t. Okay, and the Laplace transform of 1 over s plus 1 squared plus 1. But what we'll do here is use the frequency shifting property, and this will lead us to e to the minus t sine t u of t. Okay, so now we go, this is y of s again, we go to the time domain again, and what we obtain is y of t is equal to, well, this is the Laplace transform of a step, so we'll have 1, we have this expression here, so e to the minus t sine of t, and the whole thing multiplied by u of t, so don't forget the u of t here to make everything causal. Okay, so this is our solution, and now you know what I'm going to ask. Are we done? Well, no, we're not, because we have to check the initial conditions, right? Well, it's kind of obvious that y of 0 will be equal to 1. Okay, this term here will not contribute, and now what we have to do is, well, compute the derivative, and let's do that. This will not contribute, first term, so we'll have e to the minus t times the derivative of the sine, that's a cosine, okay, plus the sine times the derivative of e to the minus t, so this will be minus 1 times e to the minus t, and the whole thing times u of t. So now we can evaluate at times t equal 0. This will not contribute, this one, at time t equals 0 because of the sine, and the first term here will give us a 1. Okay, so now we are happy because our solution meets the initial conditions. Okay, so the type of exercises here that have been proposed here are the ones that you're, well, going to have at the time of the exam, at least exercises of the same type and difficulty.